Cycloalkanes, that'll be the topic of this lesson in my organic chemistry playlist, and more specifically we'll be talking about cyclohexane more than any of the rest of the cycloalkanes, and then even on top of that, specifically about the chair conformations of cyclohexane as well. Now, this comes on the heels of an entire chapter on alkanes, and we spent the first half of the chapter going through how to name alkanes, and then we've been talking about different conformations of alkanes. We went through Newman projections in the last lesson, and this lesson will specifically be talking about the conformations of cycloalkanes, and again, most importantly, the chair conformations of cyclohexane. Now, if you're new to the channel, my name is Chad, and welcome to Chad's Prep. My goal is simply to make science both understandable and even enjoyable. Now, this is my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new video. So cycloalkanes, and here we've got cyclopropane, cyclobutane, cyclopentane, cyclohexane, and cycloheptane on the board. And I want to first take a look at cyclopropane, and cyclopropane adopts the conformation of an equilateral triangle here, at least for the carbon atoms. So let's draw a couple of relevant hydrogens on here. So we got one here, and here, and here, and here, and as a reminder, the wedged bonds here so mean that these hydrogens are coming out of the board, and the dashed bonds mean the hydrogens going into the board. So, but the big thing I want to look at is the bond angles within the triangle here, within that equilateral triangle. And so for an equilateral triangle, those bond angles are 60 degrees, and that is a problem. So the carbons are all here sp3 hybridized, and being sp3 hybridized, they want to adopt bond angles of 109.5. Well, 60 degrees is not even close. So, and it turns out when your angle is much lower than what it wants to be, that's associated with what we call angle strain. Cool, and cyclopropane has a ton of angle strain. Now, if you looked at cyclobutane is pretty close to a square. It turns out it kinks, so it's not perfectly planar. It's not perfectly two-dimensional. And so these angles aren't exactly 90 degrees. They're like 88 degrees, but close enough. So, and in this case, it has a little less of this angle strain associated with it. Now, angle strain is just a part. It's one of three components of some larger topic we call ring strain. And there's two other parts to this ring strain, and there are two things that you've already visited before. One is steric strain, atoms bumping into each other, and the other is torsional strain, repulsion between the electrons in bonds. And as you recall, we studied this in the last lesson on Newman projections. We learned that eclipse conformations have significantly more steric and torsional strains than your staggered conformations. One of the reasons they're higher energy. Well, it turns out that in cyclopropane here, so if you look down this carbon-carbon bond here, you'd find out that these two hydrogens line up perfectly and these two hydrogens line up perfectly, and it is in an eclipsed conformation, and therefore cyclopropane not only has a fair amount of angle strain, it has a fair amount of both steric and torsional strain. And the combination of all three of these, we'd say that cyclopropane has a fair amount of ring strain. In fact, it has more ring strain than any of the other cycloalkanes. So, and a big part of that does come down to that angle strain. Now, if we looked at cyclobutane, that angle is still not 109.5, but it is far closer than this guy. So it turns out cyclopropane actually even has bent bonds. When the orbitals overlap to form those carbon-carbon bonds, instead of being dead on, so they're angled a little bit, and we say they have bent bonds. And it turns out these bonds are actually much weaker than in the other structures, and cyclopropane will do certain chemical reactions that none of the other cycloalkanes will do and stuff. So it's so unstable that, like I said, it's got some chemical reactivity associated with it that the others don't. All right, so it turns out by the time you get all the way over to cyclohexane here, so cyclohexane has the ability in its chair conformations to have zero ring strain. So, but it turns out that as you get smaller and smaller and smaller, you're going to have more and more and more of this ring strain associated with it. But it turns out once you go bigger than 6 carbons as well, so now all of a sudden you can't get the perfect bond angles, you can't get 109.5 degree angles exactly like you could in the chair conformations of cyclohexane. And so as you get bigger than 6 carbons in your ring, you also start encountering ring strain as well. Now we won't look at bigger too often, but we will look at this trend that the smaller the ring, the greater the amount of ring strain. And we get a little technical here. We say it has more ring strain per carbon atom is usually how we phrase it. So cyclopropane has the greatest amount of ring strain per carbon atom in the ring. All right, so because cyclohexane is the most stable by far, so it therefore is the most common ring by far, it turns out in nature and things of a sort, and it's the one we're going to study the most with the rest of this lesson. Now, it turns out cyclopropane is actually fairly common as well in nature, 5-membered rings, but it does have a little bit of ring strain, but once you get to cyclobutane, you have quite a bit of ring strain, and then cyclopropane, a ton of ring strain associated with it. All right, so now we're going to spend the entire rest of the lesson talking specifically about cyclohexane. Now, it turns out the cyclohexane can actually adopt a few different conformations, and the chair conformation is going to be the most important one and the one we're going to spend pretty much the rest of the lesson studying. But I do just want to briefly mention the other conformations, and the other one is a boat, but it's higher energy than either of these chair conformations, and this boat conformation has a couple of hydrons we often like to identify called flagpole hydrons, and if you start replacing these flagpole hydrons with bigger groups, they're going to sterically hinder each other even more and more and stuff like this. But it's one of the reasons that this is a higher energy conformation than these chair conformations. Now, it turns out there's also things called twist boats where this just kind of twists some of the angles a little bit and stuff like that. And only thing you really got to know is that cyclohexane has some other conformations besides the ones we're going to spend the entire lesson studying that are called boats or twist boats, and they're higher energy, and therefore there's not a lot of them actually present in solution. When we start looking at cyclohexane, different cyclohexane isomers and stuff like this, we're going to be looking specifically at the chair conformations and knowing that there are going to turns out be two chair conformations in equilibrium with each other, and there'd be such tiny amounts of boats or twist boats that just we ignore them entirely. So you should be aware of the names. You might get a multiple choice question somewhere along the way that says, which of the following are all conformations of cyclohexane? Boats, twist boats, chairs, done. Great, life is good. So now let's talk about these chair conformations, and we call these chair conformations. You can kind of see if we put my big noggin right there. So, and then we'll put my big feet right there, and then we'll put my arms, and I'll be reading a book right here. And so here's the head of the chair, here's the foot of the chair, so, and then these two parallel lines right here would be the arms of the chair, and so that's where it kind of gets its name. So it's like sitting in a reclining chair like so. Now, it turns out this chair is like one of those old school lounge chairs you might have had out by the pool, and you can take the foot of the chair and flip it up to where it's now in this position, and you can flip the head and flip it all the way down to where it's now in this position. And let's just pretend I was still laying on the chair after I'd flipped this side down and this side up. So now my head would be down over here. So, and I would be really uncomfortable with a broken back. So, but you can see that now when the chair converted to its other chair conformation, my head would be now at the foot of this chair. So, and then my feet would be up at the new head of the chair. And so good to go here. But the big thing here is that when we do this, we call it a chair flip. So where your head is normally becomes the new foot of the chair, and where the foot used to be becomes the new head of the chair. And then these two arms just kind of change the orientation a little bit, but they're still the two arms of the chair. So let's get me out of that picture, and I'm glad you liked my artwork, which is terrible. I draw cyclohexane chair conformations far better than I draw anything not related to chemistry. All right, so it turns out when we're drawing these cyclohexane chair conformations, they differ a little bit in how we draw them from this guy. Now, oftentimes we'll refer to this as the overhead planar conformation, and the reason we call it that way is that if we pull this off the board and turn it sideways, what we're really doing is if we looked at it kind of from the overhead view, so that's what we kind of see. So however, if we took it again off the board and held it up sideways, if we look at it from the side, that's what we'd actually see as these chair conformations. Now, on this lovely overhead planar conformation, every carbon's got two additional bonds besides the bonds in the ring. And on pure cyclohexane, those would be two hydrogen atoms. And one's a wedge and one's a dash on every single carbon. So I'm going to draw just those two in, but again, every carbon would have a wedge and a dashed hydrogen. But on the chair conformations, we don't draw any wedges or any dashes, so everything's going to be represented by a straight line, and there is some perspective that we just kind of inherently expect you to understand. So this is one of those places where I highly recommend you build a model, and we'll take a look at a model here in just a little bit. So, however, there are two types of positions we define on these chair conformations, and we call them axial and equatorial. Now, if you look at your axial skeleton includes your skull and your spine and maybe a little bit of your rib cage. That's your axial skeleton, and it runs right up the vertical of you. And so, same thing here, your axial positions here are going to be perfectly vertical positions. So if we take a look, and I'll put them on this one on the right here, if you start with either of your top two positions here, and so one thing to note, if you're drawing your cyclohexane chairs here, notice that they're made of three parallel lines. Your arms are parallel lines, these are parallel lines, and these are parallel lines. And it kind of matches what we see here. So here we've got these two are parallel lines, these two are parallel lines, and then these two are parallel lines. Three sets of parallel lines, that's reflected here as well, but we're looking at it from a slightly different perspective. So again, the arms are parallel, so these two are parallel, and then these two are supposed to be parallel lines as well. So that's kind of how you draw your chairs with three sets of parallel lines here. And then if you go to either of your highest points here and draw a bond straight up, that's your axial. So, and again, you could have started it here, you could have started here. You also could have just as well gone to your low points and drew bonds straight down. But the way it works is that then they alternate up, down, all the way around the ring, every other carbon. So this one's straight up, this one's going to be straight down, straight up, straight down, straight up, straight down. Cool, and that's all of the axial positions here. All right, so, and then every carbon's going to have one of these axials, and notice that they all alternate. 1 point's up, 1 point's down, 1 point's up, 1 point's down, 1 point's up, 1 point's down. Now we've got the equatorial, and the students don't usually struggle as badly with the axials as they do with the equatorials. So we're going to kind of look at how this works. But again, if we take this overhead planar conformation and turns it up sideways, the wedges would point up. And so what points up here, here, and here kind of like corresponds to wedges. Now the truth is, I mean, we could have, instead of flipping this up, we could take this and flip it down, and that wouldn't necessarily be true, but I'm going to flip it sideways just like that every time so that the wedges always correspond to something on my chairs that point up. Just an FYI. Cool, so this would be a wedge, and a wedge, and then these three axials would all be dashes. Now one thing to note then, if your axial position is a wedge, then the equatorial is going to have to correspond to the other bond on that carbon, a dash. But if your axial corresponds to the dash, then the equatorial is going to have to correspond to the wedge. So again, on this structure, every carbon's got a wedge and a dash, but on this structure, every carbon's got an axial or an equatorial. And the unfortunate thing is that half the axials point up, correspond to wedges, half the axials point down, correspond to dashes. And the same will be true of the equatorials. Half the equatorials will point down, correspond to dashes, and half the equatorials will point up and correspond to wedges. And the way you remember this then is that if your axial points up to be a wedge, then your equatorial is going to have to point down and be a dash. The problem is the equatorials don't point straight down like the axials. Your axial skeleton, again, runs right up the vertical of you, and that's why they all point straight up and straight down. That's why they called them axial. But your equatorials, if you actually took a look at your overhead, they would kind of be going around the equator of this molecule and pointing out. And so one would point out and up, and the next one would point out and down, but they're not going to be pointing straight up or down. They're going to be slanted up or slanted down, but also slanted out as well. And so the way you can remember how to draw these is cut your molecule in half, your chair conformation molecule in half. So all of the equatorials on the right-hand side on these three carbons are all going to be slanted to the right. All of the ones on the left-hand side are going to be slanted to the left. And then you can know if they're slanted up or down just because it's going to be opposite of whatever the axial is. So in this case, on the left-hand side of the molecule, these three all are going to have equatorial slanted to the left. And in this case, it'll be left and down because the axial pointed up. In this one, it'll be left and up because the axial pointed down. And on this one, it would be left and down because the axial pointed up. Cool, so it's not so bad. So these three are all going to be slanted to the right, and again, opposite in direction of the axial. So once again here, this axial points down, so this would be up and to the right. This axial's up, so this is down and to the right. This axial's down, so up and to the right. Cool, and you just need to get really good at drawing these. Now, one thing to note, it's these two right here that students mess up more often than anything else. And they're like, oh, I should just put it right back out in the middle of this big empty space. No, you should not. It slants left and down on this one, up and to the right on this one, not right out in the middle of the empty space. So, cool, good way to lose some points on that case. Now, it turns out when you do the chair flip, so it turns out that all of the bonds that are axial in this structure are going to end up being equatorial here. And all these ones that were equatorial in this structure, when the chair flips, become axial. And so all these ones that are red that are equatorial in this structure are going to be axial. And again, start at either high point and go straight up, then down, then up, then down, then up, then down. And we can do the same thing with these equatorials on this one. Again, they were axial in blue over here. They're going to be equatorial in blue over here. And in this case, again, the ones on the left-hand side are all going to point left, and the ones on the right-hand side will all point right. So this one, again, with the axial pointing up, will be left and down, this one left and up, and this one left and up, this one right and down, right and up, right and down. And now we've got all of our equatorials drawn in on this one as well. Cool. Now it turns out they're not equal in stability when you put a substituent axial or equatorial. It turns out, so if you've got a choice, substituents prefer to be equatorial than axial. So like if I had a substituent right here in this, where this blue one is right here, and it was axial, by the time it chair flips, it would correspond to this one right here and would now be equatorial. And what we find out is it would prefer being in this chair than in this chair. And so even though we get these two chairs in equilibrium together in the solution, it's not always 50-50. And it turns out the bigger the substituent, the more they're going to want to be equatorial. And so the idea is that you can look at a couple different things. So if we take a look at these three axials here, here, and here that all point up. So these all point straight up, and they're actually not that far separated in space. They're not that far from each other. And the bigger you put groups here, so as you know, with hydrogens it's not so bad, but you start making these bigger and bigger groups, and they're going to start bumping into each other more. And so because it's on every other carbon, and we have the same thing going on with the three that are down here as well. So every other carbon's axial position has a chance to have some steric hindrance. And it turns out it's more than just steric hindrance. There's also a little torsional strain in there as well, associated with some of the gauche interactions that happen for these axial substituents, it turns out as well. So, but as a result, we call these one-three diaxial interactions. I'm running out of space here. So 1,3 diaxial interactions. And so this is the reason we usually explain why it's better to be equatorial than axial. When you're axial, you have these 1,3 diaxial interactions. They call them 1,3 just to show that they're on every other carbon are the ones that are interacting with each other. Cool. When you're equatorial, there's nothing analogous to this that you experience. In fact, when you're in an equatorial position, you don't have any gauche interactions to worry about as well. So one thing that's nice about these chairs is that these are in staggered conformations. Every carbon-carbon bond you look down at everywhere in the structure, you'll see that it's staggered. In fact, when we look at the model here in a little bit, you'll see that. So, but they're all going to be in staggered conformations, but gauche interactions are possible. So, but only for an axial substituent, at least as long as it's the only substituent. It turns out, I mean, if you've got two adjacent atoms that, you know, in the ring that both have substituents, well, then maybe an equatorial could have a gauche interaction. So, but if like you've just got a single substituent, it'll have gauche interactions when it's axial. It won't have any when it's equatorial. So another reason it's better to be equatorial, but usually those gauche interactions and stuff, we just kind of include that and sum it up all in this idea of 1,3 diaxial interactions. So again, we got the steric hindrance between the groups themselves on every other carbon in the axial position, and then the gauche associated gauche interactions that go with it. And that's why, again, it's better to be equatorial than axial. And from here, though, I recommend you build the model. And so I'm going to take and let you guys look at a model. And again, unfortunately, my model kit is really small. And so we're going to take a look at it under my document cam. So let's take a closer look at the structure of cyclohexane here. If you look at it overhead here, we might call this the overhead planar view. Cyclohexane looks like you can see the hexagon, but you don't realize that it is not a planar structure until you kind of look at it from a sideways perspective. And it's this sideways perspective we look at when drawing the chair conformations. So we have the head of the chair here, and the foot of the chair here, and then the two arms of the chair here. Now if we rotate it one carbon over, we can adjust who we call the head and the foot. And so in this case, now we call this guy the head, and this the foot, and these would be the arms. So there's a little bit of arbitrariness, but you'll see that we've got three sets of parallel lines. We've got parallel lines here, we've got parallel lines here, and then we've got parallel lines here, and that's all part of drawing your chair conformations. Now it turns out we also have two different types of positions. I've got them diagrammed here in pink and green, and the green one here are what we call the axial positions. They point straight up and straight down, just like your axial skeleton, your skull, and your spine. So in this case, then we have the equatorial ones that kind of go around the molecule, around the equator, so to speak. So and again, if you look at it from the top view, you can kind of see them going around the equator. So and every other one slants down and then up. And so the equatorial ones here don't experience any significant amount of steric strain, but the axial ones, it turns out, if you look at them, these three all point up and are parallel to each other, and so there's some torsional strain as well as steric strain associated with that. So then the ones on the bottom do the same thing. On the bottom here, these three point down in green, experience the same thing. And since it's every other carbon, we refer to those as 1,3 diaxial interactions. So if you also look down one of the bonds here, and we're going to look down this bond right here, you'll see that in cyclohexane we're at a perfectly staggered arrangement. So
And that also leads to the stability of the chair conformation. You'll also notice that with the axial position, you have a gauche interaction with this carbon right here. So that's a gauche, 60 degrees apart. But for the equatorial positions, so in pink here again, there's no gauche with the carbons in the ring. They're pointing exactly opposite the carbons in the ring. That's another part of those 1,3 diaxial interactions. Sometimes people will mention that there's gauches there, and there's actually a couple of them for each, depending on which bond you look down. We can look down this bond as well and see that this guy's got another gauche with this carbon up front here as well. So, but whether or not we look at those or not is not the biggest concern in the world. Some people just swallow them up and just call them 1,3 diaxial interactions. But it is for this reason that it is more stable for a substituent to be in an equatorial position as compared to an axial. So let's take a look at our chair conformation again from the side view. So in this case, we got our head and we got our foot. And if you want to do the chair interconversion, so take your foot and flip it up. And if all we do is just flip it up, we'd have our boat and there'd be our flagpole substituents. So but then take what used to be the head on your left and flip it back down, keeping those arms parallel. Not the easiest thing in the world to do. In this case, I got a new chair, new head, new foot, but if you notice the difference in positions, so now it's all the pink ones that point straight up and straight down. They're the new axials, and the greens are now all equatorial going around the equator, so to speak. So, and again, if we flip it back, flip the foot back up, so, and I'll flip the foot down, and notice all the bonds rotate just a little bit, so that it's arranged in such a way that now again all the green ones are back to being axial and all the pink ones go back to being equatorial. This is your chair conformation. You should totally build a model of this at least once. You should totally do the chair-chair interconversions and see how everything axial flips to everything equatorial. One thing to note, when everything axial flips to everything equatorial, let's focus on this one right here. So this guy right here, that's axial right now in green. When I flip it to the other chair, so in the other chair, he's now equatorial right here, but he still points up. Now he's not straight up, he's still slanted up, but he still points up, and that's important, as we'll see when we start talking about cis and trans and things of this sort in just a little bit.
All right, so now that we've had a chance to look at the structure a little more carefully and see what happens in those chair-chair interconversions, I just want to accentuate again how the size of a substituent is going to affect how much it gives preference to the equatorial position over the axial position. And these are the same three that are on the next page of your study guide here. And we see that when you've got a chlorine substituent, so it strongly prefers the equatorial position so much that in the equilibrium here, 70% of the molecules will be equatorial, 30% will be axial. So, but with a methyl group, even more so, and this is not, completely intuitive. You might look at chat, a methyl group, is that bigger than chlorine? Well, it turns out, so a carbon with 3 hydrogens attached to it, so, and they're also very hard atoms, if you will, where chlorine's got a little more polarizability and it's squishier, if you will, in its electron cloud. So, but it turns out that this has an even stronger preference for being equatorial. So 95% of methyl cyclohexane molecules are going to have the methyl be equatorial, only 5% axial. So you should know that, it's more important to make sure that a methyl group gets equatorial than, say, a chlorine. So in this case, or even a bromine, turns out. Now, this is a T-butyl group here, and we see that the T-butyl group, notice, quite a bit bigger than a plain old methyl group. And for just plain old carbon chains, like it'd be more important to get an ethyl group equatorial than a methyl group. Or in this case, we see with the T-butyl group, though, 99.99% of the molecules in equilibrium are going to be in the equatorial. Only 0.01% are actually going to be axial. So the big thing here is that, again, the bigger the substituent, the more it's going to have a preference for being equatorial. So we're going to start looking at, polysubstituted cyclohexanes, and we're going to, often, the question will be asked is, draw the most stable conformation. Well, the most stable conformation is usually going to be about, this idea of equatorial being preferred over axial. But you're not always going to get to make all of the substituents be equatorial. It depends on how they're related to each other in the structure. But your goal then will be to get twofold: to get as many substituents equatorial as possible and get the biggest substituents equatorial. And it's usually more about getting the biggest ones equatorial first, and then as many as possible equatorial after that to get that lowest energy conformation. So, but just like we saw with Newman projections, one of the most common questions will be simply draw the most stable conformation. All right, one of the other important things in drawing cyclohexane chair conformations is being able to recognize cis and trans. Now, cis and trans is possible on a ring, and cis we refer to as when you've got two substituents on the ring that are on the same side. Now, in the overhead planar conformation, that means either both wedges or both dashes, whereas trans means one's a wedge and one's a dash. So here we can recognize that in the overhead planar conformation that these are both wedges, these methyl groups, so they'd be cis to each other. But again, because we don't draw wedges and dashes on chair conformations, conformations, we got to talk about, well, then how do we recognize cis and trans? Well, if you recall, we think that these wedge bonds are analogous to groups that point up. And so it turns out cis and trans therefore ends up being an up and down thing. If two groups point both up, so that's cis. If they both point down, that's cis. But if one's up and one's down, that's trans. And so we don't want to confuse this with it being about axial and equatorial, because it's not. It's about up and down. So if you notice here, this group points up and this one points up. It's not straight up because it's equatorial, but it does point up. And so because these both point up, that's cis. So notice one's axial, one's equatorial, but that has nothing to do with cis and trans in any absolute way. So if you notice in this case, these both point up, and so this is also cis. But in this case, they're both axial. So, and again, in this case, one axial, one equatorial, and it was cis. In this case, they're both axial, and that was cis. In this case, they're on adjacent carbons. In this case, they're one further apart, and that's really the difference. But again, the big thing is that cis and trans always means, you know, both up or both down for cis and one up, one down for trans. So looking at these right here, so I can see that this axial position right here is definitely down, and this one's not straight up or straight down, so it's definitely not axial, it's equatorial, but it is slanted more down than up, so they're both down. That's also another way of representing cis. So same thing on this next one here, they're both equatorial, which is not important for recognizing cis and trans, but they're both slanted down. They're both equatorial, but they're both slanted down. That's what makes them cis. So again, sometimes cis is going to mean both axial or both equatorial. Sometimes it's going to mean one axial, one equatorial. But the key is it will always mean both up or both down to be cis. Now, one of the other ways we can take a look at the chair conformation of cyclohexane is with a Newman projection. And I like to call it a double Newman projection. It turns out you can look down like the two arms of the chair at the same time. And so if we looked, you know, right down, let's do this in red. Let's say we looked right down this arm of the chair here and this arm of the chair here at the same time. What we'd find out is that the two front carbons here, be this guy and this guy, so they would be joined together down below by a CH2. That would be this CH2 right here. So, and then you'd have the back carbons that we'd be looking down right behind those two front carbons that we'd represent by the circles in the Newman projections. So, and those would be joined by a CH2 as well. And that's this guy up here. So that's kind of the perspective we're looking at. And I chose the two arms because it's easiest to see. But the truth is, as you just rotate around and change your perspective, you can look down any two parallel carbon-carbon bonds in the ring at a time and get kind of this double Newman projection. Now let's just say we wanted to look at this guy right here. Well, I can see that the front carbon, if I turn this sideways, the front carbon on the left, so has a methyl group straight up. That would be right here. So, oh, and actually we don't want to do that one. I'm going to take that back, guys. So if I want to look at one, I definitely don't want to look at this one right here. Let's see, which one would be convenient to look at? Actually, I haven't drawn, there we go. We can look at this one right here. This will be much better, and you'll see why in just a second. So we're going to look down this bond right here, and this bond right here, and here's our two front carbons, and here's our two back carbons. And the big thing here is you want to make sure that your substituents are not on the foot of the chair or the head of the chair, or else you're not going to be really able to see them from this perspective. So I want to choose one of these in looking down the arms where my substituent in this case was on one of the front part of the arm on the left arm, and the back part of the right arm are where the substituents were. So I'll be able to see both of them on my double Newman pretty easily. All right, so in this case, on the carbon on the left-hand side, I'm going to draw in the relevant hydrogen here, and the relevant hydrogens here and here. And then on this one, we've got a hydrogen here, and then a hydrogen here and here. And so if we look at the front carbon on the left-hand side, we see that we've got a hydrogen pointing straight up. So, but then slanted downward, that's where that methyl group is. So, and keep in mind, it points down. So, but the back carbon on the left, this guy right here, so he's got two hydrogens, one pointing straight down, and then one slanted upward right there. Cool. Now the right-hand side is going to be, again, looking at this perspective, it's this arm that would be on the right-hand side, and the front carbon, so again, this guy right here has a hydrogen pointing straight up, and then one slanted downward right there. And then the back carbon has a hydrogen slanting up and to the right, but then straight down it has our substituent, a methyl group in this case. Cool. And the key is realizing that this methyl group is slanted downward, so it's not axial, it's equatorial. So, but this one over here is straight down, so it's axial, not equatorial, but it still points down. So one's equatorial, one's axial, and that doesn't matter as far as cis or trans is concerned, but they both point down. Another way we should recognize a molecule as cis. And so with these double Newmans, you should realize that the positions that point straight up and down on your arms here are going to be axial, and then the ones that are slanted up or down are your equatorial. So again, axial's on this side, equatorial's on this side. Just another perspective in looking at your cyclohexane chair conformations. So now we'll take a look at several different varieties of trans isomers here. In this case, on the overhead planar, I see one wedge, one dash, and once again, that corresponds to one pointing up when you look at it sideways, and one pointing down, and that's definitely what trans is. So, and again, if we look at this on the chair, it's not about axial and equatorial again, it's about how they slanted up or down, and this one's slanted up, and this one's slanted down, and that indeed is trans. They're both equatorial, but again, the key is one's up, one's down. So here we have an axial that points down. Here we have an equatorial that points up. The key is one's up, one's down, that's trans. Same thing here, they're both equatorial, but this guy's up, this guy's down, that is trans. And then finally, this guy here, they're both axial, but this guy's up, this guy's pointing down, and that is trans. And same thing here on our double Newman projection, we can do the same kind of thing. And so in this case, I'm going to take a look once again down the arm of this chair, the two arms of this chair. So we've got our two front carbons, now we've got our two back carbons, and it's one in which our substituents are both on the arms of the chair, so it's going to be the easiest to see. In this case, on the left arm, I can see that I've got a hydrogen in the axial on the front carbon and a hydrogen in the equatorial on the front carbon. So in this case, a hydrogen on the axial and a hydrogen on the equatorial on the front carbon. And then I can see on the back carbon, I've got in the equatorial, that's where the methyl group is, and then I've got a hydrogen in the axial pointing straight down. So, and again, on the back carbon, hydrogen is in the axial pointing straight down, and then I've got the methyl group in the equatorial position on that back carbon. And then on the right arm, I can see that I've got a hydrogen in the axial pointing straight up, and then the methyl group's in the equatorial. So hydrogen in the axial pointing straight up, but the methyl group is in the equatorial right here. And then on that back carbon, got an axial hydrogen pointing straight down and an equatorial hydrogen slanting up to the right. And that's, again, pointing straight down and slanting up and to the right. And so now we've got everything drawn in on this double Newman. And what I can see from here is that this methyl group is definitely equatorial, being not straight up or down, but slanted, but it is definitely slanted up is the key. And this one's also equatorial, and it's definitely slanted down. And so just like we identified these here, one's up, one's down, they're both equatorial. So, and the key is one up, one down, that's what makes it trans. All right, so finally now we're going to draw some cyclohexane chair conformations. And again, the most common question you're going to get is they're going to give you a cyclohexane either by name or in the overhead planar conformation like I've done here, and then they're going to ask you to draw the most stable conformation. Well, that means you know you're going to draw a chair conformation. Sometimes they'll have you draw both chairs and circle the more stable one, or sometimes they'll just have you draw just the more stable one. So in my exercise here, we're just going to try and draw the more stable one. So I've got the overhead planars and I've got a chair on the board, and we're just going to do our best to add the substituents into the correct places. Now, in this case, these are both methyl groups, and they're in a 1,4 relationship. If you look, if I define either one of these as being at position 1, then the other one numbering around the chain here, whether I go clockwise or counterclockwise, it's going to be at position 4. Same thing on this one. If I make this one at like position 1, then I want to go around clockwise because I'd get to this guy at a lower number, and so this would be called a 1,3 relationship on cyclohexane, and we'll see that's going to have an impact here. Now, these are both cis isomers. We can confirm that when we're done here. So, but in this case, because these are both methyl groups, usually when I try to draw the lowest energy conformation, my goal is first to get the biggest thing to be equatorial. Well, these are both the same size as substituents, they're identical. So my goal is then just to make one of them equatorial, so if possible. So, and it'll always be possible to get the one equatorial. So in this case, it's a wedge, and a wedge means it points up. Keep that in mind. And if you look at the different equatorial positions that point up, one of them is right here. This one would then slant down. This one slants up, and this one would go down, and then this one slants up, and then this one would go down. And so those are the three equatorial positions that all point up. And I'm just going to choose one of them to be this methyl, and it doesn't really matter which one. It is totally my choice. So I'm just going to choose this one. And I've slanted a little more up than I wanted it to be, so let's just stretch that out a little bit. But I'm going to stick it right there. Cool. So, and that's going to be my number one. Let's say that's my number one. I was pointing number 4, but let's make him number 1. Cool, that's number 1. Okay, so if that's number 1, then again, in this case, I number around clockwise to get to number 4. So that's 1, 2, 3, and 4. Cool. Now, obviously, we didn't use this bond right here, and we didn't use this one right here. Now, on this carbon right here, there are 2 bonds. There's one that points straight up and axial, and one that's slanted down and left, and that's equatorial. And again, I don't get to choose whether it's axial or equatorial. I just have to make sure that it's also a wedge and points up. And on this carbon, the bond that points up is the axial, not the equatorial. And that's where this other methyl is going to go. And so in this case, I got to have 1 axial, 1 equatorial. If we do the chair flip here, well, then he'd end up being equatorial, he'd end up being axial, because they always trade places like that. In fact, let's just draw him out for the fun of it. So this carbon right here, so this would be 1, 2, 3, and 4. So 1 and 2 is still the arm of the chair. It was still the arm here. 3 was the foot of the chair. It's now become the head of the chair. So, and then 4 is right next to it right there. So in this case, this is up and equatorial on carbon 1. So, and now it's going to be up and axial on carbon 1. And oftentimes we would draw this, let's make this look a little better, and just give ourselves some room by having it kind of come over the front of that bond. So there's that one here. I could draw it real small right there if I wanted to, but I'm going to have it going right in front of, I guess actually I should make that the solid line and give this one, there we go. So it's passing in front of that other carbon-carbon bond right there. So there's one of them, and that's on carbon 1. And then on carbon 4, it points up here. It's still going to point up, but here it was axial. Here it's going to be up and equatorial. And the up position on carbon 4 here is that equatorial right there. There's our other methyl group. Cool, so notice the up-down part doesn't change. This pointed up, they were cis, they still both point up. But here, this one was equatorial, it's now axial. This one was axial, it's now equatorial. And these would have equal stabilities. It wouldn't matter which one of these we drew, because with one axial, one equatorial, and them being identical, these would have exactly the same energy, and it would be a 50-50 representation in a solution at equilibrium. Let's take a look at the next one here. So here, instead of a 1-4 relationship, it's a 1-3 relationship. And again, I want to choose one of these at the very least to be equatorial, my choice. Now, one thing we should note, so I'm going to choose position 1 here to be equatorial. We already know it points up. I'm going to make sure it gets to be in one of those equatorials again. Now, the truth is, I don't actually have to draw this out before I predict whether or not he's going to get to be equatorial as well. Because if you recall, the equatorials all alternate, just like the axials do. The axials go up, down, and the equatorials do exactly the opposite. They go down, up, down, up. And so in this case, if up is equatorial, I'm going to make sure it is, because half the equatorials do point up. So if he's going to be equatorial and up, then his equatorial would point down, and his equatorial would point up, and his would point down, and his equatorial points up, and his points down back to here. And so notice we just predicted where that methyl group's going to point. So this one, again, up is equatorial, down is equatorial, up is equatorial, which means that methyl group right there is going to get to be equatorial as well. So we can predict it without even drawing the chair necessarily. Well, let's go work that out. So carbon 1, and again, I want to make sure that I get to choose one of the equatorials that points up. So to be him, and again, it's my choice. Now I chose this to be carbon 1 on this last one. I'm going to make sure it's this one this time. This is going to be carbon 1. It's totally arbitrary. I just wanted to pick one of these 3 because these are the equatorials that point up. The other 3 equatorials point down. So cool. So I'm going to choose him to be the methyl group right here. Again, I could have chosen any one of those 3. So, and then if I numbered clockwise here, I should number clockwise here. With the 1-4 relationship, it really didn't matter one way or the other because it's equidistant around. But with a 1-3 or 1-2 relationship, you really should number exactly the same way. If I'm going clockwise from 1 to 3, I should go clockwise from 1 to 3 here. And in this case, that up position is what I need at position 3. That's that other equatorial. And so in this case, it's up and equatorial, and this one's also up and equatorial. And so if I asked you which of these two structures has the lowest energy conformation, well, this one, no matter how you slice it, you're going to get one axial, one equatorial. But for this one, in this conformation, they're both equatorial. Now, in the other chair conformation, which again, we weren't asked to draw, but let's put it in there. So in this case, position 1 was the foot of the chair. It's now the head of the chair. But now that equatorial that pointed up is now going to be an axial that points up. Same thing here, this on carbon 3 here. It used to be an equatorial that pointed up. It's now going to be an axial that points straight up. And so in this case, they're both axial. And so the one on the left here is more stable by far, by far. Now, if I said which of these two different cyclohexanes has a more stable conformation, it's going to be this one, because I do get a chance for both of the methyl groups to be equatorial. So once again, you might see this showing up as just draw the lower energy conformation, or it might be draw both and circle the lower energy. Those are the two most common ways a question like this is asked. All right, we've got two more examples to work out here. And again, this one's got two identical methyls, so I'm just going to pick one of them to make sure it gets to be equatorial. And I'm going to make sure that's this guy right here. It's going to be an equatorial that points down. And we can then predict again, does he get to be equatorial or not? So in this case, if the equatorial on this carbon points down, then the equatorial on this carbon will point up. And the equatorial on this carbon will point down, which means this wedge, that's not going to get to be equatorial. So if I make him equatorial, he's going to get stuck being axial, but then on the opposite chair, it would flip-flop. So no matter what I do here, both chairs are going to have one axial, one equatorial. Again, they'll be equal in energy. Either chair would be the lower energy one. So in this case, so in this case, I want an equatorial that points down. So the equatorials that point down are this one. So and then it's every other carbon. So as long as I make any one of those, this methyl group here, I'm good to go. And again, I could have chose either one of them. They're the same size. It didn't really matter in this case, but I'm just going to choose him. So, and if I choose him to be number 1, then I should number around clockwise till I get to position 3. So he's 1, so he's going to be position 3. And in this case, at position 3, I just have to pick whatever's up. Well, the equatorial points down. I don't get to use him. I have to use whatever's up, which in this case happens to be axial. And that's where that other methyl group is going to be. And again, in this case, in the chair flip, he's going to get to be equatorial and he's going to be axial. But either way, I get one methyl axial, one methyl equatorial. Either one would be the equal energy and the lowest energy, therefore a conformation. Now the real fun, first example we get of a tri-substituted cyclohexane. And again, you got a twofold goal if you're trying to draw the lowest energy conformation. You want to get the biggest group equatorial and the most groups possible equatorial. And in this case, the T-butyl group right here, you should recognize that as a tert-butyl. He's the thing to really worry about. These are both just little methyls. And if you recall, the methyl groups, you know, they preferred equatorial to the tune of like 95% to 5%. But the T-butyl group preferred equatorial like 99.99% to 0.01%. We really got to worry about him. His size, so his greater size than the methyls, means he really, really, really wants to be equatorial. So we got to really worry about him. So if I want the lowest energy conformation, it's definitely going to be about getting him to be equatorial. So I'm going to call him on position 1, and he definitely points up, and this guy's going to point up, and this guy's going to point down. Now I'm going to make sure that this guy gets to be equatorial on that lowest energy conformation. So, and then we can actually, again, once again, predict where these guys are actually going to be. Are they going to get to be axial or equatorial? So if in this case the equatorial points up, so then on this carbon, the equatorial would point down. Here it would point up. Here it would point down, not up. So this is going to have to be axial. So once again, equatorial points up. Here it points down. Here it points up. Here it points down. Here it points up. That's not going to get to be equatorial as well. So it turns out we're stuck a little bit. The best conformation we're going to get is going to have that T-butyl group equatorial for sure, but unfortunately both methyl groups are going to end up being axial instead. Let's draw it out. All right, so in this case, I get to choose where carbon 1 is. I just want to make sure I pick, again, a position where the equatorial points up, and it's either there, or it's there. And again, it is totally my choice, and I'm just going to choose this position right here. So that's where I'm going to put that T-butyl group. So he's there. And then if he's number 1, I'm going to number around counterclockwise 2, 3, 4. So counterclockwise 2, 3, and 4. And in this case, at position 3, I need to choose the bond that points down. Well, the equatorial pointed up. It's the axial that's going to point down. There's a methyl group there. And then at position 4, I need the bond that points up, which is another axial. The equatorial pointed down. And so again, we're stuck with both methyl groups being axial, but the T-butyl group being equatorial. But this will be much lower energy than if these two had got to be equatorial and he'd got to be axial. Again, with that T-butyl group, no ifs, ands, or buts. If you got a T-butyl group on your cyclohexane, make sure he gets to be equatorial, again, if you're looking for that lower energy conformation. Now, if you found this lesson helpful, consider giving me a like and a share. Pretty much the best thing you can do to support the channel. And if you're looking for practice problems or the study guides that go with this lesson, check out my premium course on chadsprep.com.